Alright, so let's continue and try to finish off 1806. And I think we left off at lecture 27. So this one is on positive definite matrices, or the principal axis theorem. So, okay, you've got to understand like what is a positive definite matrix and why do you need it in the first place. And so you start off with a 2 by 2 matrix. So suppose you had A, B, B, C, like this, right? And so there are two ways to test that this matrix is positive definite. The first way is with the eigenvalues, right? And so if lambda 1 is greater than 0, so if the eigenvalues are positive, then your matrix is positive definite, right? And lambda 2 is greater than 0. So this is like the first test. The second test would be the determinant test, right? And so you kind of have to take the entire determinant though, so like both the 1 by 1 determinant and the 2 by 2 determinant. I understand that I haven't really gone over that determinant chapters yet, and I'm thinking to put it off again because it's like 1806 is not a trivial course by any means, right? And so surely it's only 3 lectures, and determinants is a very small part of linear algebra now. But okay, like take 17 to 20, like if this determinant stuff is still confusing you. But okay, you take the 1 by 1 determinant, right? And so A has to be greater than 0, that determinant needs to be positive. And you also take the 2 by 2 determinant, right? And so that's, what is the 2 by 2 determinant? Well, in this case, it's quite trivial, right? It's just AC minus B squared. So I don't think that's AC minus B squared. That shouldn't be, well, not AC squared, it's just AC minus B squared. And this needs to be greater than 0. So this is the 2 by 2 determinants. And if both of these are greater than 0, then your matrix is a positive definite, right? And there's a third test as well, which is related to the determinants, and the pivots, right, need to be greater than 0 as well. So this first pivot here, right, A needs to be greater than 0. And the second pivot, how do you find the second pivot? Now this is where it can get a bit tricky, but the determinant, you should know, the determinant is the product of the pivots. So this is another way that if you knew your pivots, you can compute your determinant, or vice versa. If you knew the determinant, you can also find a missing pivot if you wanted to. The determinant is product of pivots. I'm not gonna write that entire thing out. And so, okay, what does that mean? Product of the pivots, like, that's a bit strange, isn't it? Well, it's A times B, right? So let's write out what this formula is trying to say. The determinant of this entire thing is AC minus B squared, right? So the determinant of the 2 by 2 matrix is A times B, and well, we know what A is, so we're trying to solve for B, and so therefore B would just be AC minus B squared over A, right? It's just a simple transposition. And so this quantity as well, this is the pivot, right? So this is the pivot, the second pivot. This quantity needs to be positive as well. So these are all independent tests for whether or not a matrix is positive definite. But the definition really is this new expression, x transpose AX being greater than 0. Okay, and this is the principal axis theorem, and we'll get into what that means in a bit. But if this expression comes out as true, then most certainly you can go and check all of these independently as well. But this really is when you say a matrix is positive definite, then this is what you mean, right? Or at least, at the very least, positive semi-definite. If it's equal to 0, that's the marginal case where it barely fails, right? Then it's positive semi-definite. But we'll get to that. So let's get to that actually straight away. So the example is 2, 6, 6, and 18, right? We've got a symmetric matrix here, but it barely fails. Like if you look at the test, right? First of all, you can look at the determinant test, for instance, right? And you'll see that it just barely fails this test. So it's 0, right? So what does this mean? like 2 by 18 is like 36, right? Minus 6 by 6 is 36, is 0. But it needs to be positive, right? We said we're looking at like the determinant test in isolation here. But we said it needs to be positive, so we're looking at the marginal case to try and understand what happens at this particular case, and then we can see, okay, how is it going to completely fail, and like when is it good? When is it any good? Well, obviously it'll be any good if this number here or any higher, right? If this was 19, 18 is our marginal case, 17 certainly fails, and anything over 18 is definitely positive, definite. Okay, so let's look at x transpose ax, right? And so this is just, I think you should be able to like work this out by now. You've got a vector x1, x2, right? And then you transpose this guy here. So you got your vector 1, 1, 2, x1, x2, like it could be anything, right? You transpose it and then you multiply by x. I don't know if maybe I should just like x1, x2, right? This is what I'm trying to get at here, right? So I hope you see what this means. Like, so you do x transpose a, right? Or you can do ax. So the sensible thing to do would be ax, right, and then do x transpose. Yeah. So this makes a lot of sense. And so let's do this ax computation first, right? And okay, this is just a times some vector x1, x2, right? Because we just transpose that vector over here. And what you're gonna get is this matrix here. So 2x1, and you can like carry out that multiplication if you wanted to. 6x2, 6x1, and then 18x2. So it's fairly simple. So this is x transpose ax, right? This is ax here. And this is x transpose. And this thing needs to be greater than 0. Like, what is this exactly though? So let's carry out this here. And what you're gonna get is 2x squared. Okay, it's very simple. It's just matrix multiplication. Like nothing fancy is going on here at all. Plus 18x2 squared, right? And this here is in the form, right? If you look at this very carefully, you can say this is ax squared, right? This is the general form, plus 2bxy. If you look at it very carefully, 2bxy plus cy squared, of course, greater than 0. Okay, and so this is for all x1, x2, right? And ax is linear, but x transpose ax now is up to degree 2. If you look at this is like a purely quadratic, right? And so you need to evaluate this function somehow. You'll probably know from calculus then that the way you just look at the second derivative of the function to decide if you have a maximum or a minimum, right? Because the first derivative alone is not sufficient, right? But I think the proper way to see this is with completing the square, because like it's so obvious, right? Okay, it's obvious from calculus too, but it's like super obvious here. So you have your function, right, f of x, and we're going to change the problem. We're going to change from our marginal case 18, right, up to 20. So we're going to go to a matrix that we know is certainly positive definite. So that means the only thing we're changing here is this value here. Let's suppose we change this from 18 to 20, right? Well, the function would look pretty much the same, right? So it'll be 2x squared plus 12xy, right? Plus, instead of 18 now, it'll be 20x squared, or 20y squared, x2 squared, but this time we like substituting y instead. So it's just to make the notation a little bit nicer, but it's really the same thing. But now you can factorize this. How would you factorize this, right? So we're looking for a sum of squares, right? So we need some x and we need some y, right? So obviously we need two of the x's to get back this here, so we're good there. And how do we get back the 12xy, right? Well, this is fairly simple. We just put a tree here, right? I hope you can like see this binomial expansion. Yeah, I'm not gonna go into what that is. And then we need 2 of the y squared, right? Okay. And this would complete it, right? And why do we need 2 of the y squares though, right? So tree y will give you back the 12xy. That should be obvious. And then after that we'll have 18, right? 18y squared. And so we need to add back in, right? That, remember, 18 was the marginal case. So in the marginal case, this is 0. We don't need to add back anything else, right? But now, right, we do have to put in something else here, right? We do have to put in back the 2y's to get to the 20 that we injected into the problem, right? And so the point here, right, is we have a sum of squares. That's the point. And if you have a sum of squares, then your quantity can be never negative, right? Like, it's never negative. Like, it doesn't even matter if you had a negative value in here. You square it, it's going to become positive, right? So your matrix is positive, definitely. But what does that even mean, right? Like, that's probably something that's so... I need to show you the principal axis theorem like straight away. Let's look at this problem. So if we took like a cross section, right? So set this equal to 1, right? So we're taking like a cross section. What is this gonna look like? So you have something like this, right? And so you have your function here, right? Your quadratic form, and you have your minimum point here, right? And so we like if you took like a cross section, you set it equal to 1, it would something like this, right? And so this is an ellipse, right? This is an ellipse. And the idea here is that completing the square is exactly Gaussian elimination, which we've been doing like all the time up until now. But like, how is this Gaussian elimination? Like, if you look at these values very carefully, these values are not, let me change the color. These values are not random. This 2 is not random. This 3 is not random. This 2 outside here is not random either, right? The pivots are outside and the multipliers are inside. And so I wonder if they did give an example. Oh yes, of course, there's always an example. My notes are just so nice. Like, the shorter handwriting is like absolutely atrocious, but you can make it out if you know your stuff. Like, but if you didn't know, like, this would be hell actually. Anyways, there's 1806, so there's no better place to go. My notes are no substitute for 1806. Okay, so if you look at this, right, 2, 6, 6, and 20. Oh, right, this was the original matrix that we started with. Of course, like, yes. And so if you look at this is obviously a pivot, right? That's a pivot sitting outside there, right? And the other pivot, so if we put this into upper triangular form, right? Put this into upper triangular form, what are we going to get? We're going to get 2, 6 zeros below, right, and a 2 here, obviously, right? So we're just trying to eliminate below the pivots, and you should be familiar with how you do this by now. And the L, right, so if you're going for like A equals LU, the factorization, so the L, what is the L? So the multiplier here is 3, right? And it's sitting right here, like, this is the multiplier, 3, so it's like 1, 0, 3, 1. Right, so if you had A, right, if you had L and U sitting right next to each other, this is the exact multiplier that you would need. You would need 1 of the first row, right, and 3 of the second row precisely, and 1 of the second, like 3 of the first row, I mean, and then 1 of the second row back to get back this original matrix. So here, if you put this L right next to this U and you left multiply in terms of row operations, you would get 1 of this, so you recompute the first row, right, and then 3 of the first row now, right, so that would be 3 of this guy, so you would get the 18 here, right, and then obviously you put that back in there. So yeah, it's pretty straightforward, I feel like. So it's 18, and then the 2 would give you the 20, and then 2 by 3 is 6. So I hope that's clear, and it's not like too convoluted. And you're probably wondering, like, why is this tree like sitting here? It shouldn't be like -3, but remember, right, -3 would probably be the elementary operation. Remember, we had these elementary operations before, but then we did an ALU factorization. So the matrix is not over here; it's over here this time. So it's like the inverse, right? And so yes, it's 3. So yeah, it's exactly Gaussian elimination, right? Okay, and so we did an example for 2 by 2, but here's the beauty of linear algebra. Linear algebra isn't 2 by 2 or 3 by 3. It's n by n. You can like jump up, so you understand what's going on, obviously, on the lower dimensions. But now you can go to much higher dimensions because you understand the concepts will carry over much the same, right? So if the pivots are greater than 0, right, then we end up with a sum of squares, and yes, of course, the graph is gonna go up, right? And can you see like why the pivots are important then? Like in the marginal case, right, where this was 0, where there's nothing here, there wasn't a second pivot. Like that was the problem with the marginal case, right? You could not get a second pivot, and so your matrix would fail in terms of positive definiteness. Like not completely fail, but you know, not the best. And then obviously you can see if the value was actually less than the marginal case. If we had 17 here, for instance, then you would need to put in so this is the problem now. Here we're adding in back the numbers, right? But now if you went below that marginal case of 18, you would have to subtract away, right? And so it's no longer a sum of squares now, because this negative sign, right, is going to tell you, okay, well, this graph is no longer positive definite, right? We're not just purely going up, and so that would be a problem, and so it would completely fail in that example. Okay, so I think there's one more example here that tries to make things concrete, and so we have 2, -1, -1, 0, and -1, 2, -1, and 0, -1, 2. Right. And so you do your x transpose ax on this thing, and what are you going to get? Okay, so it's a really convoluted expression, and I don't want to go through all of the working, so I'm just going to copy. Should I just copy the result? Is the result even necessary? Well, sure, yeah, I think the result is the entire point, so you can like carry out this x transpose ax if you wanted to, like x transpose ax, and we've just seen how to do that. This is just now from 2 dimensions to 3 dimensions, so it's nothing complicated there. So 2x squared plus 2x2 squared plus x3, right, third component, and then this is minus 2x1 x2 minus 2x2 x3 is equal to 1. So we took the cross section again, right? And so instead now, instead of an equation of an ellipse, since we're up into 3 dimensions, this is the equation of an ellipsoid, right? And this is the whole point of the principal axis theorem. Here, I think, is where you kind of see it. So, like, what does this look like? You're gonna have like something coming like this, right? And then another, it kind of looks like an eye in a way, right? And you're gonna have a major axis, right, like this. You're gonna have a major axis. You're going to have a middle axis, like here, right? So this is your middle axis. And you're gonna need one more. You're gonna need a minor axis that comes through from here. Can you see like what's going on here? So this is your minor axis. Like, what does this mean though? And so the axes, right, are in the direction of the eigenvectors. That's the really nice thing. And the length, of course, of these axes is determined by the lambdas. And so principal axis theorem, again, is just A is equal to Q lambda Q transpose. If your matrix was, in fact, positive definite, then obviously you can take your vectors, right, and get an orthonormal basis, right? If you have an orthonormal basis, then you can get this Q lambda Q transpose factorization, which is like really is the best factorization for like any one given matrix, right? If it was as good as this, right? Obviously, if your matrix is not positive definite, you know, and it like fails in like a million different ways, then you're gonna have to use something else, which we'll see later on, called singular value decomposition, which is very closely related, by the way, to this factorization right here. Just slightly different. You'll see what I mean by that. Okay, so that should be fairly straightforward. I feel like. So insert page after. And so lecture 28, I think, started off by discussing this notion of positive definite matrices a bit more. Okay, yeah, and like where does this entire like notion of positive definiteness come from? And it comes from like least squares and like rectangular matrices, like any kind of physical problem really that you have. And you really do need to do a bit of applications to see. Right now everything is like, you're sort of being taught everything in a vacuum, but it's a good vacuum. You can trust like your vacuum in this case. Normally, when you're learning something, right, you're like, oh, this is like so abstract, and how does this apply? But like, it's not so hard to see in this case, right? Anyways, the point being, like, what about A transpose A? Like, you know, what is A transpose A, and where does it come from? And that's like, I don't know if you remember from the least squares problem, like what this A transpose A business meant, right? Like if you had X, right, AX, for instance, equals B, and you do A transpose AX equals, you know, A transpose B, then, you know, you're good to go, right? So, yeah, I don't know if that's making any sense or not, to be honest with you. But I don't want to go over back the entire projection chapter. Like, we already did all of that. So anyways, let's look at this X transpose AX, right? So we're assuming this is our new A now. But anyways, this is how you would make your matrix symmetric, right? If it wasn't, like, you had a rectangular matrix. Like in this particular case, if you had tall and skinny, or if you had fat and short, okay, if you want to put it that way, tall and skinny is like something like this, right? Then you'd want to make this into a square n by n matrix by putting A transpose over in this side, and you'd be good to go. And so this is like, can you see like what's going on here? Like, this is the same thing as AX transpose AX. And so this is the length squared, right? This is like X transpose X. Like, I hope you remember that from the projection chapter as well. X transpose X, like, always is a length squared. And we just spoke about the length squared. Like, what does that mean, right? So, okay, yeah, so it's always positive, right? And so that's why this like A transpose A business is like a sort of a magic combination if your matrix looks like this, like tall and skinny. So what does tall and skinny even mean, right? But we'll see like in a bit later on. I think I have some stuff in my notes. I hope. We'll see. But I might as well like explain what it means now. It means that your matrix is full column rank. Full column rank. It means there's nothing in the null space of your matrix. Right? So that's like very important. So there's a pivot in every single column. Right. That's the point. And I hope you can see like what that means in terms of the principal axis theorem. Like, you should be able to do a little bit of critical thinking here as well. Okay. And then we moved on to the concept of similar matrices and this idea of a Jordan matrix and the Jordan form. It's not terribly important to know, actually. This was like linear algebra, maybe, oh god, maybe like 40 years ago or something. Like, it's not as like relevant today, but of course it's good to know. Right, and so what is a similar matrix? A similar matrix is in this form: B is equal to M inverse AM. If you have a matrix in this form, then A and B are similar, and you should recognize this. Like, this should be familiar to you. If you remember, S inverse AS is equal to what? Lambda. So lambda and A are similar to each other, right? And so in this case, right, instead of the S's, right, or the eigenvector matrix, you could take any M, and it would come out similar to A. But lambda is like just the best form, and this form is what's known as the Jordan form, or the Jordan matrix, right? And the point about similar matrices is that they have the same lambdas. Like, why though, right? Why is this the case? So we start with the only thing you know, basically, which is AX is equal to lambda X, right? And like, we've got this up here that we're working with in terms of like the definition of a similar matrix. And so what you can do, right, is you can say A M times M inverse X, right, is equal to lambda X. We didn't do anything here. We just like stuck in the identity matrix here. But it was quite clever in that now we can multiply on the left by M inverse, right, by M inverse. And now you've got this form B. This is B. I hope you recognize this is B. Some vector, right? This is a matrix times a vector, which is going to produce a vector, right? So we'll call it V for vector, is equal to, right, M inverse lambda X. Like, can you see like what's going on here? Okay, you can move this lambda, by the way. So you can, it's like, this is lambda. I should make it like a little bit more obvious. M inverse X. Now it should be like super clear what's going on here. Like, can you see? It's okay. Like, this is the same definition as AX equals lambda X, right? Some matrix times a vector, right? This is our vector here. Some matrix times a vector is going to produce, right? That vector, right? But just scaled, right? So they have this, the point is they have the same eigenvalues, but not the same eigenvectors, right? This is not m inverse x, right? It's not the same as x, right? The eigenvectors here are different than the eigenvectors here, okay? And so that's the entire point. And so let's see. Oh yeah. So there's like more notes on why the eigenvectors change. I don't think I want to go into that, to be honest with you. It should be clear. Like, it's obviously clear here that the eigenvectors are not the same thing. Okay, and so I do have a geometric interpretation to the principal axis theorem as well, but it's quite lengthy. It looks like it's like 3 pages or something. Okay, this was for me to at the time. Of course, as I'm saying, like, this is not trivial stuff, and you need to work with the material to like really understand what you're doing, right? So, but I'll like try to stick to like the main themes of the lecture. And so there's a bad case of what happens when we have a repeated lambdas, right? Like, what does that mean? Like, so do you remember like we had this matrix S, like, and like if we didn't have a full set of independent eigenvectors, right, then we wouldn't be able to diagonalize that matrix, right? And so that's the issue here. And so the idea is, right, you've got these family of matrices, and so if you had, like, for instance, I think the first example was 4 0 0 4, right? And this guy is obviously diagonal. Like, look at this and see. And if you factored out of 4, right, m times m inverse would just, like, you can look at this matrix, factor out the 4, right, and m times m inverse would just give you the same matrix back, right? Like, if you put m inverse here, like any m inverse, and you put m over here, factored out the 4, the m and the m inverse would look at each other and turn into the identity. Identity times 4 will give you back this original matrix, right? And so this is like the only member of this family. But then there's another family of matrix which would like be much bigger. For example, if we had 4 1 0 4, for instance, right? This is called the Jordan form. And this is like the best form. You can look at this 1, right? And this 1 could be any value, right? So that's the point. It could be 1,000,000, it could be 1,000, it could be anything. But the 1 is sort of like the best family. This matrix is the best one. Like, you could find an m over here and an m inverse over here, and you can find like a related matrix to this, right? But this one is like the best one in the family. And so this matrix is not diagonalizable because lambda equals 4, right? It has an algebraic multiplicity of 2, but a geometric multiplicity of 1. At this point, I hope you understand what I mean by geometric multiplicity. I want you to think principal axis theorem, right? Only one vector, like, in the eigenspace, I guess is what I'm trying to say. And so the lack of diagonalizability means it cannot be simplified to a sum of squares, okay? And okay, we've seen like what this means in terms of like principal axis theorem and that sort of thing. The only time like a repeated lambda could work, right, is in this case here. If we had like a sphere, right, the last time we had an ellipsoid, but if you had a sphere like this, then yes, of course the length or the lambdas are going to be the same, right? Yeah, like that makes sense, right? So, but okay, like these things are all connected together. And the point of what is this Jordan matrix I'm like yapping about all this time? So like an example, so there's like 0 1 0 0. Yeah, I remember he was like making a joke about like poor like Jordan was a good guy, but you know, he had to work with these really, really ugly matrices. Okay, so like you've got this matrix here, right, and then you've got another, let's take another one right next to it. So like 0 1 0 0 0 0 0 0 and 0 0 0 1. Like, this is really horrible matrix, by the way. Oh god help you if you had to work with this. Okay, it's not too bad, but like certainly wouldn't prefer it. And so if you were to chop this up, right, into Jordan blocks, it would look like this. It would look something like this. And the point is, right, that these two matrices are not similar because, like, from this visual perspective, right, the blocks are not the same sizes. Like, this block is 3 by 3, and then you have a 1 by 1 in the corner here. And then this block right here, like, you're looking at these two blocks, right? Forget about the zeros. So this block over here is just like not you know, they're not the same size. These ones are equal, but this one is like much bigger than this one. So you can conclude safely that these matrices are in fact not similar. And so every square matrix A, so this is like what it means like to be a Jordan matrix, right? It's similar to a Jordan matrix J, right? And so the eigenvalues will sit on the diagonal, but they're just one, like just above them, right? And so the best Jordan matrix is actually, you've already seen it, it's a diagonal matrix, right? Where you've got these Jordan blocks, so it looks like this. J is equal to like Jordan block number 1, Jordan block number 2, all the way down to Jordan block number n, right? And the best case is where J is equal to lambda, right? And okay, the not so best case, we've seen, like you just put a 1 like just above where your eigenvalues sit, right? And so these are like numerically a nightmare to compute, right? Kind of like algebraically it's nice to see the idea, but it's not good algebraically. Like it's very similar to this Kramer's rule thing that I was telling you about earlier. Still haven't gone over the determinant chapter. Oh no. Anyways, very similar to that in the case that yes, it's nice algebraically, but if you really wanted to compute the inverse using anything sensible numerically, then you would use Gaussian elimination, of course, right? Okay, and I think I went into a little bit more of the nitty-gritties here, and I think I'm just going to like share that insight with you as well. It's nothing like earth-shattering, it's obvious, but of course it helps to go over these examples. And so this is a pivot, by the way, right? And so the eigenspace is one-dimensional, I think is the point with this matrix here. And so if we had A minus lambda I x equals 0, so we're trying to solve this characteristic equation. And so obviously you need to start by finding the lambdas, and you're going to, I hope you know how to do this. You're going to end up with 4 minus lambda squared, and then obviously lambda equals 4, so we have a repeated lambda, right? And so, right, so that's the whole point. So the null space, right, is actually one-dimensional. It's a one-dimensional null space. So you're going to get 0, 0, 1, 0. I hope you're following. If you're not following this, then I think you might need to recap on the earlier chapters. Okay, so this is your null space. It's one-dimensional. Your eigenspace is one-dimensional. But if you contrast this with the other example we had before, like with 4, 4, 0, 0, right? Your null space, your eigenspace is actually two-dimensional in this case, right? Because you don't have this value like sitting here kind of like screwing things up for you. And so you do have a basis for the entire null space, really, right? You have a basis for that whole two-dimensional space is the point. And so the basis would just be 1, 0, 0, 1. And you're good to go. Right? You're good to go. And those, that would actually just be your eigenvectors, right? And then we said before, then this would be like the perfect example where you did have this sphere, right? But it didn't matter that you had the repeated lambdas, because you have like these eigenvectors which give you the principal axis, right? And the lambdas are just so happen to be the same size, right? Because it's a sphere, obviously. But in this other case, it was just not so, right? Okay, I hope that's clear enough. Now we go on to the singular value decomposition. This one, I think, I might have to do like another video on the singular value decomposition at another time. But at the very least, I think I can give you the main ideas behind the singular value decomposition. But it really is the heart of linear algebra. Like everything you've been learning up until this point is to do the singular value decomposition, right? And like the last generation of scientists and engineers were sort of using like this Fourier transform, which we did before, the fast Fourier transform, as a way to convert, because you can change we haven't done linear transformations as yet, so I don't think you understand what I mean by change of basis. But okay, the point being that you can tailor down to a specific problem, as opposed to having like some general piece of machinery that you pass anything through, right? You can actually get a tailored solution or a tailored basis for your specific problem. That's the whole point of the singular value decomposition. Okay, and like it's applied, oh god, it's used like everywhere. It's crazy. Like, and here's the thing, right? I was having a conversation with the professor the other day about this, And it's like, you shouldn't try to look at it like, if you're being taught this by like a computer science person or something, right, they will confuse the hell out of you, because they're gonna teach you, or somebody who does data science or whatever they're doing with the SVD, right, or in my case I use it for robotics, right, they're gonna confuse you because they're going to indoctrinate you with their particular context, right? Context is going to be very important to this, like, or how it's used, right? And you're going to be so confused because you're going to see, oh, it's being used like this here, and it's being used like, and you're like, what does this even mean, right? And so you have to try to strip away all of the external context and really understand the mathematics, like from first principles, as he called it, like a strip back engine, right? And once you understand that, then you can build at any given time. If you're learning a new context, it's just going to be the same thing repackaged, right? Okay, so like, here's the point. The point is, right, if you had some vector in the row space, right, so let's say, had some vector in the row space like this, and let's call this v1, and we had like some other vector over here, we'll call it v2, it's also in the row space, and these two vectors are orthogonal to each other, and then we can obviously normalize them, so we can get an orthonormal basis for the row space, I guess is what I'm trying to say, right? And we had something else here in the column space, some vector over here in the column space, and we can call it u1 or u2, right? So let's say like this is u1 and this is like u2, okay? And these are also perpendicular or orthogonal to each other, and so the row space is like a times, so okay, so a times v1, I think it's better if I show you this way. A times v1 is equal to like sigma 1 u1. Like, how do you write sigma? That's the thing. I think it's sigma's like this, common sigma, something like this, right? Sigma 1. Forgive me if this sigma is wrong, but I think it's exactly like this. Sigma 1 u1, right? The point is, like, we're working with the entire basis of SVD is an assumption, really, and we have no reason to believe that this assumption is true, but turns out it is true, actually. So this is the assumption, and then so A, right, some linear transformation, some function, something is multiplying, right, this first vector, and it's producing, right, a multiple of this basis vector. Do you see that? I hope that's clear. And then again, A times v2 is going to multiply on this vector and produce like some multiple, like, okay, so sigma 2 u2, right, of this other basis vector. So do you see what's going on here? We have an orthogonal pair of vectors that are being operated on in one space, right, in our row space, and somehow we end up with an orthogonal pair of vectors in the column space. Now that's like pretty special, right? That's very special, actually. And so that's the assumption we're making here. And so what you end up with is a times v, right? So if you wanted to, like, let me make this clear. So a times v1, v2, all the way up to vn, right? And so you can see how this multiplication would distribute, right? So this is AV, right? This really is just AV, right? You want to package these vectors into a column of a matrix. Like, this is what you do in linear algebra, right? Come on. At this point, it should be no surprise that that's what we're doing. And okay, what are we getting on the other side? Well, this should be like fairly straightforward. We're getting the u's, u1, u2, all the way to un. And okay, on the right, so this is on the right, I'm sorry, there wasn't enough space here, but the sigmas sit on the diagonal. Oh god, I really should like invest in something to write with. There should be something, right? An iPad or something might work, because this mouse situation is just not helping me at all. So sigma 2, sigma n, right? And like you can see, like, you take linear combinations of the columns of this matrix, you're gonna get sigma 1 u1, sigma 2 u2. Like, this should be fairly straightforward. So what is this though? So this is u times this matrix sigma, right? And we said that this is this matrix, right, is orthonormal, right, or it's orthogonal. It's an orthogonal matrix. Then obviously its inverse is quite easy to compute. It's just v transpose. So this is the singular value decomposition, u sigma v transpose, like this. This is like the magic sauce that we're working with here. And so now we have to look at this matrix, this magic matrix, A transpose A, right? So any matrix, so this is the point now, any matrix can be decomposed into this singular value decomposition, right? Before we were looking at like how do you like diagonalize a matrix and stuff like that, but this works for like just about any matrix, right? It doesn't matter. You can just, it just works, right? And I'm sorry that I didn't, in retrospect, I personally probably would not have put this lecture at, I believe this is lecture 29. I would have put this at the very, like, just towards the end of the course. Okay, it's at the end of the course, and it's fine the way they did it, but I do feel as though it's important to understand, because there's context here concerning the left inverse, the right inverse, and the pseudo-inverse. And you do need the singular value decomposition to compute the pseudo-inverse, but I feel as though it's important to teach the left and the right inverse, because you see this A transpose A transpose business, but you'll see it here as well, so I don't think you're in too much trouble. Okay, let's look at this A transpose A situation. A transpose A, what is this, right? Okay, well, we know what A is, so what is the transpose of this guy? Can you like figure out what A transpose is? Like, if you're taking the transpose of this matrix, right, it's going to come in reverse order, right? So you're going to get a V, right? Look, I hope you see what's going on here. Can you see what's going on here? I don't know. But I hope you know, like, at this point, like, what's going on here. So A transpose A, right, is equal to, I'll just write it out for you. So V, right, sigma transpose, because like if you transpose a matrix, you're taking it in reverse order, right? Like this should be clear. If you're transposing a product of matrices, it comes in reverse order. So this is V transpose transpose, which is just V, sigma transpose U transpose, right? And then A, right, which is just U, I'll use a different color, I'll use like this red, which is this U sigma V transpose. And what you have sitting here, my friends, is the identity. Like, this is what it means for two matrices, like, to be, this is the definition of like Q transpose Q, right? Like an orthogonal matrix. This gives you the identity, right? So this is gone. And sigma transpose, this is a diagonal matrix, so it's just sigma. So sigma times sigma is sigma squared. And so the factorization becomes V sigma squared V transpose. Look at that. And so this, A transpose A, this is your Q lambda Q transpose for A transpose A. And so the singular value decomposition really is like just like a combination of two square matrices where you have the eigen, you'll see this in a second, but you have the eigenvectors of like two separate square matrices, and their eigenvalues are like sitting in the middle, right? But like how is this like an eigenvector, you're probably wondering. Look at this, right? Let's try to bring over let's multiply both sides by V, right? So A transpose A times V is just, okay, so if we put a V here, it's gonna go, right? And we're just gonna be left with V sigma squared. And so this should be like super familiar to you. This is, what is this? This is like very similar to AX equals lambda X, right? So this guy is your eigenvector, and this is your eigenvalues here. I hope that's clear at this point. And so V, right, so we've seen now that V, it really is just the eigenvectors, right, of this A transpose A matrix here. And we said, what is A transpose A? A transpose A you use, right, when you have like a matrix that looks like this. That's like tall and skinny, right? And then if you did like A transpose A, and like it looks like this, you're gonna end up with an n by n matrix like this. And then the other case then is, so we've seen how to get the V's, right? And you do the like the very opposite thing. You do A transpose. A transpose is gonna come in the opposite order and is going to knock out, this time, in this case we knocked out the U's, right, to get the V's. But if you do A transpose now, you're gonna put the V's in the middle and you're gonna knock those out, and you're gonna end up with very much the same thing. So you're gonna end up with the eigenvectors for U, right? And you have the eigenvectors for V, and okay, it's not, yeah, the eigenvectors for V, it's not too difficult to get the eigenvectors for V transpose. Come on, it's fairly simple, right? Let me put on the lights. Okay. Right, and so that's the basics of the singular value decomposition, right? And so, yeah, okay. So it's, I hope like it's like clear enough. obviously this is not all. This is like, okay, this is like a basic understanding of what's going on. So you can come back and look at this, right? And this would be like the singular values. So here, if you notice, it's the same sigma, right? We end up with the same sigmas, whether or not you multiply like with A transpose or do AA transpose, you're going to end up with the same sigmas. But this time for the singular values, it would actually just be like square root, right? Because notice that this sigma value here is squared. Okay. Alright, so I think I should stop here, but the point is that this really is like the perfect like Q lambda Q transpose, right? That we ended up with here. Q for this matrix, A transpose A. But I want to go on now to linear transformations. I think this is like a fairly brief but good way. This is your strip back engine for your singular value decomposition, right? And then there's so many other ways that you can look at this. But if you understand like fundamentally what's going on here, you're good. I'm actually going to come back to this later on, and we're going to do a complete example, because normally you don't want to compute this thing with AA transpose and then A transpose A. Numerically, it's a nightmare. You're going to have to do some QR factorizations and things like that, and there's also like a little bit more context as well that you need around this, but you've more or less got what you need, right? So let's move on to linear transformations. So like, what is a linear transformation? So I'm trying to like really hurry this along now. So transformation is defined as and so normally your course would begin with linear transformations, but I really like the way in which they organize this. They put it towards the end, which is really nice, because you do get to see, because you've been doing like so much, you have so much experience at this point with matrix multiplication that like you'll see that matrix multiplication really is defined in terms of a linear transformation. Get some water. Okay, so your transformation looks something like this. T, right, takes some input vector R2, right, into R2. This is it. So it's a mapping really from one space to another space, and so your mapping obviously needs to be defined by a rule, right? And so you can think of a transformation that behaves like exactly like a function. And so I think the first example was that of a projection, which we've been working with quite a bit now. I've got a meme about this. Okay, I'll show you the meme later on. It's so funny, like once you see it. Anyways, so imagine we had some vector here and like we projected it down into the space here, right? So that's like, this would be T of V, right? Then given an input, the transformation is obviously going to produce some output. Your input is this vector V, and the transformation is T of V, this output, this point on your subspace or your basis for a column space or whatever you're working with, right? And so there's some rules for linear transformation which are quite simple. The first one would be T of V. They're so like obvious, man. V plus W, right, is equal to T of V, right, plus T of W. Like, what is this? The transformation of two, so you have two parameters, V and W, right? And if you're adding them, then obviously it's going to be, it could be like you do the individual transformation on the first parameter and then you add the transformation of the second parameter. Like, okay, it's like very straightforward decomposition going on here, right? So this whole thing is like the same thing as if you did the transformations like one at a time and just added them together. And then T, the next one is T times CV, right? Right, so you have some scalar quantity times your input, right? So your parameter is going to give you the transformation on that vector, yes, but with C factored out. Like, do you see what's going on here? It's like a scaling factor then, right? And then you can like kind of bundle these two rules together into one. And so really the one ring to rule them all would be C times V, like any scalar quantity times V, plus D times W, right? Any scalar quantity times your vector W is going to give you, like, you should be able to see this, right? It's the same thing as this guy up here, but this time with the scalar pulled out, right? So C times T of V plus D times T of W. Okay, like fairly straightforward, I feel like. And then obviously, I feel like this should go without saying, but it's trivial, but it's not so trivial. It's very important, actually. T of 0 has to be equal to 0, but like, you can see why T of 0 is 0, right? Come on. But okay, it's like, it's worth mentioning. Like, if you didn't have this rule, then yes, certainly you don't have a linear transformation. Alright, so an example, a non-example, I think will help to cement this. If you have some vector, like this V, and your transformation rule was to shift the entire plane by some vector v0, right? So this is not a linear transformation at all. And the point is, okay, so the transformation would look something like this, where you have your vector v first, and then you shift it by some vector v0, and your transformation looks like this, right? But if you double the transformation, right, so if you said, okay, if you double this vector here to this guy, and so now you have t of 2v, right, instead of 1v, right, you don't get 2 times, like, remember you can pull out this, oh, I wrote v twice, 22v, no, it's 2v, oops, sorry about that, okay, but you can pull out the scalar, right, like we said before, pull out the scalar, and you get t times v, right, so it's the same transformation, but just, like, scaled up. But this is not the case here. Like, if we double this vector here, and then we apply the transformation rule, which is shift the entire plane by some vector v naught, this guy would end up, like, somewhere here, right? But can you see that doubling this input parameter did not double the transformation, right? Do you see the original transformation took us here, right? And so you would expect, like, if you were to double this, it would be, like, much further out, right? So that's the point. So this is not a linear transformation. Okay, so another example would be the 45-degree rotation. So, like, let me put another page. So 45-degree rotation. So your rule, obviously, your transformation is taking all of R2 into R2. You always need to define, in terms of a linear transformation, what your input space is, what your output space is. And, like, you can very clearly see, like, okay, if you're doing, like, this vector v here, right, and then you do a 45-degree rotation, it probably ends up here, right, t of v, and then you can check to see that, okay, well, if I double my input parameter, like the size of this vector, right, the transformation, like, will also double. Like, do you see? Like, it's pretty straightforward to see, like, what's happening there. So yes, this is a linear transformation. Alright, and so now we start to work with examples with matrices, because, you know, this is linear algebra. And so t of v, right, is equal to a times v, is the point here. Like, this is why I was always sort of, like, referring to our matrix A as, like, some kind of linear transformation, right? Or some kind of function, really, if you want to think of it as, like, a mapping. And so the same rules will apply, really. So a times v, okay, v plus w, right, is, okay, should be a times v, right, plus a times w. Like, okay, this is, like, fairly straightforward stuff. It's the same set of rules, again, just repackaged this time to sort of accommodate this matrix A that we've been working with the entire time. And so c times v is just c times a v1. Okay, same rules for linear transformation, and then a of 0 is obviously, well, 0, right? And, like, you should see very, very, very clearly, like, why a of 0. You give it a zero vector, no combination of the columns of a will give you the 0 vector, obviously. So, like, 0 times anything will take you to 0. Okay, like, this is trivial, right? Okay. Yeah. So there was an example here. Okay, I don't think this example. Okay, it's like, it's trivial, man. You already know what this matrix A means and what it means to multiply a matrix by a vector. Okay, and so the idea of a linear transformation, as we've already established, really is an abstract description of matrix multiplication, right? And so, so imagine we have this transformation here, T. So we're taking vectors in R3, right, into R2. So this is, like, really good practice, I feel like. This is the rule, right? Or this is the mapping, I mean. And the rule, we've got to try to figure out, like, what is the rule, really. So we know T of V is equal to A times V. And we're trying to figure out, like, what is this matrix A, right? What is this matrix A that is going to, like, take vectors in R3 and give us vectors in R2, right? And the way in which you do that is A is going to have to be a 2x3 matrix. Can you see why? Like, our vector, our input space, so start with what you know. Or we know our input space is in R3, right? So our vector is going to look something like this, right? This is our input vector here. And so this is 3 by 1, right? So we know that this guy, right, in terms of symmetry, it needs to be something by 3, right? It needs to be something by 3. So this matrix here needs to be something by 3. It needs to have 3 columns, at the very least. It needs to have 3 columns, right? and the result needs to come out in R2, right? So the result needs to be the result needs to look like this, right? So now we need to figure out how do we complete this matrix. And the point is that obviously you need to, the vector for this matrix A needs to be in R2. That's the point. And so that when you take linear combinations of the column space, right, then yes, obviously you're going to produce something in the column space which is in R2. And so the column space of your original matrix needs to be really the column space of your output. I hope that's the point really I'm trying to make. And so you can sort of like retrograde analysis, I think is what you call this. You can sort of work backwards and construct what you need if this method suits you. Obviously there's like probably a million other ways you could like reason this out for yourself. Anyway, so this is like 2 by 3, and so you end up with a 2 by 1 matrix. And yes, this is indeed in R2. So you're good to go there. Okay, and so how much information do you need to know about the transformation to like figure this out, right? Oh no, something. Okay, now we're good. The limitations of our tools. I wish like this didn't happen though. To be honest with you, like I just want it to be like on a single page. You know, this is too much to ask for. I suppose it is too much to ask for. Oh, okay. Well, we'll like skip this page and like work on the left hand side then, because like I don't want to go over there. Okay. Suppose then you knew your input vectors, right? Like TV1, TV2. So this is the point. If you know, right, what the transformation does, right, to every vector, every basis vector that you have, right? This is the point. Then you know what the transformation does for all vectors in the space, because you can take linear combinations of the basis vectors to produce the entire space, right? Like we've seen this idea many times before now of like independence, basis, span, dimension, like all of these things are like tightly coupled together. Okay, what do I mean by that? And so I suppose an example will help. So if we had V is equal to C1 times V1, right? Plus all the way up to Cn times Vn, right? This is fairly simple, right? You know what the transformation is going to do to every linear combination then. Okay, so this is like, I don't think this is too difficult. And so if you had T of V, right, T of V, and you should like recognize this by now, right? You can pull out this scalar factor here, right? And so what you end up with is C1 times the transformation on the first basis vector. Like, do you see what's going on here? All the way up to Cn times the transformation on the nth basis vector. So this is like all pretty straightforward. Okay, and so there's only one way, right, to express V as a combination of the basis vectors. I hope you're trying to see what I'm getting at here. So these numbers, here's the point. These numbers are your coordinates, and so let's do like a concrete example to sort of like cement what I'm talking about. So if you had a vector, right, 3, 2, 4, and this is like, I think this is probably the downside to seeing this idea of linear transformation so late in the course, is because all the while we've been working with what's called the standard basis, right? And so the basis here is, what is the basis? It's 1, 0, 0, right? Plus 0, 1, 0. Like if you had these 3 orthogonal vectors, they constitute a basis for the entirety of R3. Like if you took any linear combinations, can you see here now? See any linear combination of the first basis vector. So any vector is expressed, right, as a linear combination of all of the basis vectors, and these C's are what produces the coordinate system. So from the very moment that you have a basis for your vector space, right, then you've introduced coordinates to the system. And so to get this particular vector, you would need 3 of the first basis vector, 2 of the second basis vector, and precisely 4 of the last basis vector. Can you see that? And so that's what the coordinates mean. The coordinates are defined in terms of the basis vectors, right? And so, but this is the standard basis, which would be, but this is not like the best. It's like terrible basis actually. Professor was like hogging on me. He's like, yo, like move away from that nonsense now. Yeah, like fine. Okay. So I think this is like fairly straightforward stuff then at this point. Alright, and so we need to construct a matrix that represents a transformation from Rn to Rm, right? And so you choose an input basis for Rn. So, okay, so choose an problem. Let's see, problem. Construct a matrix A that represents T from Rn to Rm, right? And so first of all, you choose an input basis for Rn, right? So you can call that V1 up to Vn, and you choose an output basis for Rm. We'll call it like W1 to Wm, right? And so what does this look like? This will look something like this. You've got your, and we can use like the same basis actually. And so in this particular case, the basis vector will be for both spaces, right? Because it's, so V1 is going to be W1 is what I'm trying to say. So V1 is W1 and V2 is, V2 is W2. Alright, and so V1 is a unit vector on a line, okay, it's chosen as the first basis, and V2, second basis vector, obviously it has to be perpendicular to the first one. Okay, this is like fairly straightforward. You know, if you have two perpendicular vectors, then they constitute a basis for your space, and you've seen this already with Ram-Schmidt, like for a million different reasons. Okay, and we choose an output basis. In this particular case, we just happen to make them the same, right? And so V, right, V is equal to C1 V1 plus C2 V2, right? Some vector, right, has to be a linear combination of these two basis vectors. Okay, we've seen this idea before. So take any vector V, it's some combination of the first and second basis vector. And so T of V is equal to C1 V1. And so the second base, so the second basis vector is killed. And so I think the problem here, why is the second basis? So this, I don't have it in my notes, but this is actually, I can infer that this is the, we're trying to construct some kind of projection matrix. Is this what we're doing here? Oh yes, most certainly. I think this is what we're doing. And so yes, and so if you look at this very carefully, if you took the first vector V1, so this is what we're trying to do. We're using a projection matrix, right? And you applied it to your first basis vector V1, what's going to happen? Well, by the definition of a projection matrix, you're going to get back this. You're going to get back that. However, if you applied the projection on the second basis vector here, V2, it's going to kill that vector. It's going to take it to 0, right? And so that's the rule that we're trying to find. And so the output needs to look like this. The output needs to look like C1 and 0, right? This is what our output needs to look like. Okay. Alright, this is like fairly straightforward. And so the matrix here is actually just 1, 0, 0, 0. Yeah. And so if you multiply this by C1, C2, then you're going to get C1 and 0. Okay, this is fairly straightforward. And this is like, yeah, okay. There's nothing too complicated going on here. And so I suppose this is just an example. Alright. And we can obviously, we've been talking about basis now for quite some time, and so the best basis actually to use is the eigenvector basis. But it's not, I say best, but it might not always be the case, like as in, you'll see later on in the next chapter. I'm not going to go over the entire image compression example, but I'll just like give you some of the main points. Okay, so rule to find A, right? Given a basis vector, right? And you have an input, V, and you have an output W. The first column, you apply the transformation to it, right? And then for the second one, you just apply the transformation again, and you'll be able. We'll do an example in a bit, and this will kind of like make sense. Okay, and so really neat application of this like idea of a linear transformation. The derivative is a linear transformation. Like this is how I like to think of the derivative actually. And so you have a basis, right? So this is why you can have like a small set of functions like sine x, cosine x, e to the x, and like, you know, a small set of functions, relatively small set of functions that constitute a basis, right, for this space. And then if you take all their combinations, you can get all the derivatives. And it's so nice. Like, it's so nice. Like, come on. Anyways. And now I think we go over to lecture 31, which is change of basis, right? And so we've met the fast Fourier transform. Actually, have we met? Yeah, we did an example on the fast Fourier transform, I think. But at least I think I at least explained what the fast Fourier transform is, right? And so some vector, if we had some vector in the standard basis, right, it can be expressed as a linear combination of another basis, I think is the point here. So if we had some vector P, right? In our standard basis, C1, W1, all the way up to C8, W8, right? Or CN, WN, whatever you want to call it, right? This vector, this coordinate system, currently we're assuming, right, is in the standard basis. But suppose, right, we wanted to convert over into another basis, right? Change of basis. What would you do, right? How would you do this? And so, what you do is you take W times your coordinate systems, like C1 all the way up to C8, and this gives you P, right? I hope this is like clear. And so your new basis is going to come over here. In this particular example, for image compression, I think he was using the wavelet basis, which is like not too far off from the Fourier basis, right? And what you need to solve in this particular case, right? So P is equal to W times R, right? Fairly straightforward, right? And so we can find out what exact linear combinations we need here. And so C is just going to be W inverse times P. And here's the reason why you would normally pick like an orthonormal basis, right? Because we can very easily compute its inverse, right? You just transpose a matrix and you can very quickly find that change of basis, right? So it's usually pretty fast, right? And so this is really good if you want to compute the new coefficients in this new basis, really. Okay. So there's the example now. Like this is the part that's like really important, I feel like. And so given a basis V1 to V8, what is A? And so if you know what the transformation does to every basis vector, like T, so if you know like T of V1 all the way up to T of V8, and we've seen this idea before, right? Then you know what it does to every linear combination of the basis vectors, right? And so every x, right, is a combination of the basis vectors. And so x is equal to C1 V1. Like we've seen this already, right? C8 V8. Every vector x can be written as a linear combination of the basis vectors, so long as it's in the space, right? Okay. Fine, yeah. And so T of x, and okay, this is just like repeating what we've seen already. C times T of V1 all the way up to C times V of T times T of V8. So it's fairly straightforward. And so this is really, right, the transformation done on all of the basis vectors at once, right? And so this is just T of C1 V1 all the way up to C8 V8, right? So this is just a transformation being done on the entire vector. This is just expanded form, this is contracted form. And so you can factor out the scalar, and so it really is just a linear transformation. So if you double the input vector, T also doubles, right? But why? So you also have to ask yourself why. Well, exactly because you're doing the transformation to each basis vector like at a time. But you're just changing the scale. You're just changing the coordinates. Like, can you see like that's what's happening really? I really hope you do see the point. Like, but okay. Let's do an example with the eigenvector basis, and this should like sort of to help cement things here. So let's get another page going here. So T times V sub I, right, is equal to lambda I Vi, right? So AX is equal to lambda, or AV in this particular case. Remember we said the transformation we thought of like as AV if you wanted to think of it that way, right? But the transformation on this ith basis vector is equal to the basis vector, right? So this is the input space, this is the output space, right? And you're trying to figure out like what is A? What is A, right? And so the first input vector is V1, and so we're like working with knowns and unknowns, right? So let's start off. Our first input vector is V1, and the output is lambda 1 V1, okay? And so we write the output, right, as a combination of the basis vectors, and so it's lambda 1 times V1, and like none of the others, right? Can you see like what's going on here? And so we found the first column of our matrix A, and it would just be lambda 1, right, and none of the other basis vectors. And this is the point I was trying to make before, right? Like, do you see this? Okay, let me like extend this idea. So the second input vector is V2, right? It would be V2, and the output would be lambda 2, right? Lambda 2 and V2. And so So v2 lambda 2 v2. And how do you get this? How do you get this? Well, obviously, right, you need, like, you know, one of lambda 2 and none of the others, right? So just, this is exactly the amount that you need. And so this would go into the second column of your matrix A, right? And so let's extend on this idea. And so T, the transformation on V1, right, would be like A11 times V1, right? Plus A21 times V2. Like, do you see what's going on here? All the way up to like AN2 times Vn, right? Or AN1 times Vn in this particular case. And so the lambdas of the first basis, right, unlike none of the others, that's the point, right? So you need lambda of the first basis vector and none of the others. So this is like, this should be pretty straightforward, I feel like. And so for this one, it's just a transformation applied to V2. And what are you gonna get? You're gonna get A12 times V2 plus A22 times V2 all the way up to AN2 times Vn, right? And so you need lambda of the second basis vector and none of the others. And so A, what is A? A is just lambda. That's the point. So if you continue this trend, you would just get all the lambdas sitting on the diagonal here. And so, yeah. Okay, and you see the point now that lambda is equal to S, like S inverse AS, right? Can you see what's going on here? And notice that these matrices are similar as well, right? And so the transformation with a different basis, right, will have different matrices, but they're going to be similar. I think that's the main point. And so we had like a transformation T of like V1 to V8, right, has some matrix A, right? And then we have the transformation with the wavelet basis, T W1 to W8, has like some other matrix, we can call it B, right? But these matrices are related to each other. And they're related to each other in that A and lambda are in fact similar, right? And so I hope like you see the entire point of what this is, right? And so this is how we were able to construct this matrix A, right? Given our input space and our output space. So can we like sort of recap like what's going on? So you write the output as a combination of the basis vectors, right? So it's lambda 1 times V1, right? Write the output as a combination of the basis vectors, right? And so we know what the output is, and so to get that output exactly, you just need, like, you know, one of lambda 1, none of the others. So I think that's like very elegant and quite straightforward actually. Okay, and so there's the last lecture in the course. Do I have any water left? Oh no. Almost done. Like we're like coming to the end of this course now. Okay. No, come on. Okay, here we go. So we can probably put it here, right? And so I'm gonna touch on the left and the right inverse, and I'm gonna leave the pseudo inverse for another time. Okay, so two-sided inverse you've probably met before, right? A times A inverse gives you the identity, and then you can just do it in the other order. You can go in A inverse times A, and you would still get the identity. And this is for the case where the rank is equal to M is equal to M, right? This is full rank. You've seen this before. Now let's talk about full column rank. Full column rank is when you've got like this tall and skinny matrix. What does that mean? R is equal to N is less than M, right? So the rank is the same as the number of columns in your matrix, right? So it's full rank means that you have there's nothing inside of your null space, right? And so what does that imply? If there's nothing in your null space, then it means that you've either got a particular solution or you've got no solutions at all to the system, right? But you do have a pivot in every column, right? So there's a solution or there's no solution. And so A transpose A in this particular case will give you an n by n symmetric positive definite matrix, right? And so if A is full column rank, then A transpose A is also full column rank. And this is like the really nice fact, right? And so how should I do this? Like, okay, if A transpose A is like full column rank, it's symmetric positive definite, means it's invertible, right? It's invertible. So we can find A transpose A inverse. So we can compute A transpose A inverse, like this, right? And then we can multiply that by its transpose times A, and this will give the identity. Can you see what's going on here? This is the left inverse. All right, so first you start off with A, right? Your tall and skinny matrix is full column rank. So you do A transpose A. A transpose A in this particular case is invertible. So we find the inverse of A transpose A. We multiply that by A transpose. And the point is you can move the parenthesis here. And so A transpose A inverse times A transpose A. I hope you see like what's going on here. And this is going to produce the identity. Alright? And this is the right inverse. This is the left inverse, I mean. And the right inverse would be, for the other case would be full column rank, right? So your matrix is now like short and fat, right? Your matrix looks like this. And then you do have something in your null space sitting over here, right? And so R is equal to M less than N, right? Okay, this is fairly straightforward. And so your null space of A transpose is just like the 0 vector. Fairly straightforward stuff here. Okay, and so the rows in this particular case are independent, and so the solution always exists, right? But because there's something inside of your null space, then there's an infinite number of solutions. I hope you remember that. To find a particular solution, it's just some x particular that you find plus like your entire null space. And like you can see in this particular case, instead of having to do A transpose A, you have to do A transpose, right? So A times A transpose is the magic combination here. And then you multiply that by A transpose inverse to produce the identity. Like, I hope you see, like, so now instead of like doing it on the left, you put it on the right this time. This guy here is your inverse for A, right? Because, okay, you move your parentheses, you can see like very, very clearly what's happening here. It's very much the opposite case. Okay, but what happens when you put, like, let's look at this first example with the full column rank. Like, let me move over here. What happens like if you try to put the left inverse on the right? Like, so A, instead of putting the left inverse over here, what if we put it on the right? Like, what if we had A transpose A inverse times A transpose? What is this? This is a projection matrix. You should recognize this as a projection matrix, actually. I hope you can see that. Like, this is a projection matrix. Like, if we had like AX x hat equals b. I'm just gonna like do a brief review on the projection chapter. Then you would do, right, you multiply both sides by A transpose, right? And so we've seen like where this comes from before. I'm not gonna go over the proof for this. And so x hat is just gonna be what? A transpose A inverse A transpose V. Okay, I hope this is like starting to come together now. So therefore, right, AX hat, A times X hat is just A multiplied by A transpose A inverse, and then A transpose V. Okay, so all we did was stick the A out in front here. And, okay, let me change color. And so this portion here is your projection. Like, do you see it's the same thing? This and this is the same thing. Right? This is equal to P times V. Or AX, however you want to think about it. And so what you're doing really is you're trying to project this vector V down into the column space, right? And so you can think of it like this. For any vector, right, that exists in your column space of A, then there exists, like we'll think about this in a second, there exists some X, some vector X that exists in Rn, right, such that V is equal to A times X, right? Well, what is this? What is this trying to say? For any vector which exists in your column space of your matrix, right? So this is any, so suppose our column space was a plane, right? The entire column space was a plane. So any vector that exists in that plane, for any vector in that plane, right? There exists a vector inside of Rn, right? So it's the same dimension, right, as your column space, right? Rn is your column space. Then yes, there exists a vector x inside of a column space such that, right, V is equal to A times X. So you can take any linear combination of the columns of the matrix, right? And you'll be able to find there exists an X such that there exists a linear combination of those basis vectors that can give you a vector inside of the column space. I know it sounds redundant, but this is like kind of how math is like written, but that's what this expression is trying to say. And so you can look at it like this, like P times V, right, is, okay, well, we're just gonna substitute in our projection matrix here. So A times A transpose A inverse, and then A transpose AX in this particular case, right? So this is P and this is V, we said before, such that V is equal to A times X, right? So okay, I've already explained what that means. And so you can like, okay, this is like, here's what you can do. You can move some columns around here if you wanted to. And it's like so nice, you know, it's just so nice. But okay, if you move the parentheses around, what you'll find is AX is actually just equal to V, which we've like proven before. And the point of this is that if you had a projection, right, on some vector that's already in the column space, it's not going to do anything. The projection is just going to stay right there. That's the entire point of this. And can you like see where the parentheses are going here? I hope you can like figure out where to put your parentheses in the right orders here. And yeah, so like A transpose, right, and then A inverse. Okay, it should be fairly straightforward, like what you have to do here. I'm not gonna like tell you that, but A transpose A inverse A transpose A is gonna go, and you're gonna be left with this part is gonna go, and you're gonna left with AX. So I'm just gonna show you that, okay, in case maybe you struggle to figure it out. Okay, so that's the entire point. Okay, and then you go on to pseudo inverse. Pseudo inverse is like the worst, okay, not the worst case, but the most general case. And so now you don't have full column rank and you don't have full row rank either, right? So there's something in the null space, and then there's also something in the null space of A transpose as well. The whole point is, the thing that's like screwing up the inverse is, right, like if you were to do this, right, this matrix here, if when we try to post multiply, it's not going to work, right? The matrix is trying to be the identity, but it can't be the identity because the dimensions don't match, right? It's going to project the identity where it can, right? And zeros are going to appear everywhere else. It's like you have like a 3-dimension, like you're in R3, you're in 3 dimensions, right? But your column space is just a plane, right? And so you can only do so much, right? You can only work within the plane. Like, so even though like your space exists in R3, you're still confined to that plane. Okay, so I hope that's like at least a little bit insightful. And so this does give you like a little bit of idea as to where this A transpose A business comes from the singular value decomposition and the AA transpose. Like it comes from this tall skinny matrix, right? Which is full column rank, and then we've also got this short and fat matrix, right? And that's full row rank. And so the singular value decomposition will allow you to compute a pseudo inverse where you sort of like just throw away your null space. Your null space is so the null space of A and the null space of A transpose is what's like screwing up the inverse, right? Because if there's something in a null space, then yes, there's some linear combination of the columns of A that take you to the 0 vector, and the inverse could never recover it, right? Like it's dead. So if you can like throw away the null spaces, like the point, then yes, then you can get the best possible result, which is called the pseudo inverse. Okay, but we'll probably do like an example later on, but not now. Kind of tired. Okay, and so there's only like one thing left to do now to like completely like finish this course, and it's to do a numerical example with the SVD, and that'll probably be best served with the pseudo inverse. And then then there's a chapter on the determinant. I think I'm just going to forego that chapter entirely. It's lecture 17 to 20. Like determinants used to be like a really big part of linear algebra, but now it's just like really just a tiny portion. And the cool applications for determinant is like volumes, right? Like instead of like memorizing a bunch of formulas for volumes or area or anything like that, you can just compute the determinant and it gives you the volume. That's the point. But geometrically, you do need to see why, which is why it's important you go do those 3 lectures. But maybe I'll do them later on, maybe not. Anyways, so yeah, that sort of brings us to the end of things here, really. So yeah, I think we can call end there.